Hello, my name is Gabriel, and I'm going to continue from where Katrina left off on data preprocessing. As she rightly mentioned, data preprocessing can really help you improve the performance of your machine learning model. She discussed so much about audio data, and in this part of the recitation, I'll be focusing more on image data. So to get started, we'll be using the Pillow library, which is an image manipulation library from Python. And we'll also be using Touch Vision from PyTorch for easy data augmentation, which is done using PyTorch Touch Vision transforms. So to get started, we will download some random images on the internet. Of course, they are open source. You can get them from Lorem Pixum. And this code, we download some three random images. And after downloading the random images, then the first problem which you would face, it's about the problem of the images having the same sizes. So it's difficult to guarantee that all the images you would want to feed into your model will always have the same sizes. However, your most deep learning models require some fixed input dimension. If not, then you would be dealing with incompatibility problems. So in this code, we're just resizing all the images which we downloaded to ensure that they have the same size. In this case, the size is 224 by 224. Of course, we could do this with touch vision transforms, but this is the longer way, and hence we'll see that using PyTorch touch vision, it simplifies this process. Next up, after resizing our images, then we would actually want to see how our images look like. The reason being that uh, sometimes we might have like wrong images inside of our problem. So we can think if we're dealing with an image recognition system and then we have a picture of this, which is just like a sea and no face, then it's definitely a wrong image and it will just spoil our model. As Katrina mentioned above, if you have bad data, then you would have a bad model. So it's good to have a look at the images and see if they actually match what you expect. So after visualizing the images, then the first of the transformations which we will do is the normalization. In order to normalize, we need to calculate the mean and standard deviation of each of the channels in the RGB, since we're dealing with RGB images. So here is a helper code which helps you to calculate that. And what it does, it takes a data loader as a parameter. So if you're not very familiar with datasets and data loaders, I recommend you watching the recitation about datasets and data loaders. After calculating the mean, we're going to make use of PyTorch touch vision transforms. And here we applying the normalized transform, which means we want to normalize all our data using the mean and standard deviation, which we calculated above. So here we apply the normalization transform and we get this result. So typically you will not get this because the idea behind normalization is that most of your images they are similar, so getting the mean and standard deviation of the images will not be very different from a typical image inside of your dataset. Uh, Next, we would try some other data augmentation strategies, which is key in making your model robust to overfitting, because we are often faced with less data. So it's good to provide our model with more data, but more data could be difficult to obtain. So in this case, we transform the data which we already have so that it behaves as if it is a new data into our model. So here I am applying the random horizontal flip with a probability of 1. Normally you will not do it with a probability of 1, but because I want to ensure that the images are flipped, so I set it a probability of 1. And here we can see these are the original images and below are the augmented images. So this appears like a new image in our data set, and we can see the direction of the guy moving across the street changes. So in a pedestrian detection system, this image will still be a valid image in our data set. However, inside of our original data set, we didn't have this image. Same with the image on the facial recognition. So this person over here, they have now a new image which represents them being flipped. So this is still a valid image in a facial recognition system. So we've basically increased more data and make our model robust to overfitting. PyTorch touch vision transforms also permits us to combine multiple transforms using the compose function from the transforms. So we could always combine multiple of these transforms, but it's, however, important to note that not all transforms are valid. So you should understand your problem and understand the kind of transformation you're applying. So it will be very common to see the first of the transforms being the resize transform. As I mentioned, this is to ensure that your shapes, your input shapes match the input of your model. And you could have some other transforms like the horizontal flip, which we've seen above, the color jittering, affine transformation, and to converting them to tensor, and also the normalization transform. So it's also important to note that there are some other of transformations because of the various data types. So here, once we are applying the resize transform on our raw data, we are having a pillow image. But to apply the normalize, we need to have them in tensor. So we should apply the to tensor before applying the normalized transform. More can be understood by reading PyTorch documentation about the transforms. So here, applying multiple transforms, we can see here there is a horizontal flip, there's color jittering. Here there is also a horizontal flip, there is color jittering. But however, if we notice, if we have a problem where we want to detect like maybe if there is a C in the image or not, then this color jittering doesn't help us because the color becomes a very important property. So again, it's important to understand what problem you're solving in order to know the right data augmentation transformations to apply. And let's have a look at one of those transforms that might not be suitable for some problems. So if we think about a facial recognition system, then a, uh, a vertical flip might not be a very good transformation because we don't expect people to come to appear in front of the camera upside down or something like that. So it's of no point making our model robust in detecting this orientation, which is not common in real practice. And this will conclude our session about image transformations. And here we have some self-assessment questions to test your understanding of the pre-processing concept. So one of them is yourself, asking yourself, why is the mere spectrogram a preferred feature over the raw spectrogram? So think about it. Think about why we are actually doing this pre-processing. Like what are we doing? Think about the human perception of and every other thing. So some of the times the pre-processing steps will involve some domain knowledge, and hence it's important to research about your data. So another question is, or what is the significance of applying the frequency and time masking as a transformation in the audio data preprocessing? So do we have problems with signals? Can we sometimes do we have missing signals across the time domain or across the frequency domain? And augmenting this our data set by masking some of them, does it mimic the real life situation and make our model robust? So you should think about that. And also same goes with the image transformations like flipping, rotation. What could be their benefit, especially in computer vision tasks? Okay, thank you for watching, and please feel free to post any question on Piazza or send us an email about this recitation.